Good morning. In this lesson, going to talk about osmosis as the last lesson in the unit of pharmaceuticals. What is osmosis? It's when water or solvent flows from lower solid concentration into higher solid concentration. The level of the solution with the higher solid concentration rises, and the concentration of the two solutions becomes equal with time. What does that mean? Let's consider a case where you have a osmosis apparatus. Here I have a beaker. In the center of the beaker, I have a semi-permeable membrane. A semi-permeable membrane is a membrane that allows for water molecules to pass through to both sides very easily. But at the same time, solute particles, that's those yellow spheres over here, cannot pass. So a solvent can pass a semi-permeable membrane, but a solute cannot pass. So what happens here is that if you look at the apparatus to the left, right now, in the right side of that container, I have a high concentration because I have a lot of solute particles, but very in comparison to the left. So the left side is very low in concentration. And that's not ideal. Over time, if you put a semi-permeable membrane in the center, the water molecules from the left side of the solution will start migrating to the right side of the solution, but the solute particles will stay in an attempt to equilibrate amongst themselves. So over time, what will happen is that the solution to the right, the water level will increase. And the process of osmosis is especially important for biological systems. I start building by the premise that most physiological solutions in human body contains 0.9% sodium chloride. That's 0.9 grams of sodium chloride in 100 milliliters of solution. And also it contains 5% glucose or 5 grams of glucose in 100% solution. And those concentrations are ideal for human body. And let's consider a cell that's a red blood cell. If we place a red blood cell in a solution that matches the physiological solutions, they're equal in concentration, and the cell would not change or undergo no change. And this type of solution is called isotonic solution. In other words, an isotonic solution for human body is either 0.9% sodium chloride or 5% glucose. Now, let's consider a solution where the solution concentration is less than the cell concentration. So I'm going to say solution concentration, SOLN for solution. The solution concentration is less than the cell concentration. That word is supposed to be cell. That kind of solution is called a hypotonic solution, where the solution concentration is less than cell. What will happen is that water molecules will flow from the solution into the cell, and the cell will undergo hemolysis, where water flows into the red blood cell, causing it to swell and burst. So imagine that if you inject a solution of, say, 0.1% sodium chloride, that's very low comparing to physiological solution into a patient's body, their red blood cell is going to burst because of the low surrounding concentration. And if you have a solution that has a higher concentration than the cell concentration, so in the case of a hypertonic solution, hyper means higher than, so my solution concentration is greater than the cell concentration. Water will actually flow from the cell out to the solution. And water will leave the red blood cell, causing the cell to shrink. And what will happen is this process of crenation. and neither of which is ideal in medical settings. So in summary, we can see that when cell concentration is greater than the solution concentration, we have hemolysis, or in other words, the cell will swell and burst. When cell concentration is less than the solution concentration, the water from the cell will flow into the water, and the cell will shrink in the process of crenation. And in the ideal situation where the cell concentration is equal to the solution concentration, the cell will undergo no change. So question, most IV solutions used in a hospital is isotonic, hypotonic, or hypertonic solution, and why? Let's pause the video for a moment and think about your answer. Let's consider an example. Describe each of the following solutions as isotonic, hypotonic, or hypertonic. Indicate whether a red blood cell placed in each of the solution will undergo hemolysis, crenation, or no change. Let's look at solution A. I have a 5% mass over volume glucose solution. So let's compare that against my physiological solutions. 5% mass over volume glucose is isotonic to is the physiological solution. So therefore 5% is equal to 5%. I'm going to say that this is isotonic, or the cell's happy. And the corresponding cell will undergo no change. Let's look at case B. We'll have 0.2% mass over volume sodium chloride solution. Let's look at our chart for physiological solutions. In order to be isotonic, we need 0.9% sodium chloride. So in this case, 0.2% is far less than 0.9%. So I'm going to say that the solution concentration is less than the cell concentration. So therefore, I'm going to quantify that as hypo, or qualify that as hypotonic. What happens in a hypotonic solution? Or what happens when a cell concentration is greater than the solution concentration? The water molecule will actually flow into the cell and it will cause the cell to burst. And this process is called hemolysis. And finally, the other application is called dialysis. Dialysis is when a semi-permeable membrane permits small solute particles and ions and water to pass through, but retains larger particles such as colloids. What is a colloid? Larger particles such as DNA and protein are examples of colloids. And that's helpful when we try to isolate protein or isolate DNA. We can place this in a dialysis bag and then in a solution of pure water, for example, the smaller molecules and ions will actually exit out of the dialysis bag. And inside the bag, there'll be a small amount of those particles, but mainly colloids such as DNA, protein, or starch. And very soon you'll be watching a video on the application of dialysis. But that's the end of this lecture.